Okay, let's take a look at a numerical example of the DHO. I have written the relevant equations here on the board. When it comes to the position of the DHO as a function of time, we're not necessarily concerned with the cosine at this point, because after all, that's just describing the oscillation. Instead, we're more concerned with the amplitude term, that is describing the exponentially decaying amplitude as energy as lost as heat. That's this expression here that describes the amplitude as a function of time. Okay, so let's go ahead and access the numerical example. Please copy it down into your notes. Let me read it to you here. Okay, so a 1 kilogram mass undergoes damped harmonic oscillations where the spring constant K is 100 newtons per meter and the damping coefficient B is 0.25 newton seconds per meter. Alternative units are kilograms per second. Okay, let me go ahead and write down these values and show you where those units of B, the damping coefficient, come from. Okay, so first of all, the mass M is a kilogram, spring constant K, 100 newtons per meter, and then we have B, 0.25, first of all, newtons seconds per meter, or alternatively, kilograms per second. Okay, depending upon the textbook, you're going to see the units of B as one or the other. Your textbook writes it as newton seconds per meter. Some older textbooks write it in the following way. Here's where those units come from. Okay, recall that the damping force is B times V. The damping force itself is in terms of newtons, and then we have B, and then multiplied here by speed, which is in terms of meters per second. If you move the seconds up to here and the meters down to here, then you end up with newton seconds per meter. If you write newtons, however, from F equals MA as kilogram meter per second squared, then some cancellation occurs and you end up with kilograms per second. However, more times than not, you're going to see the units of B, the damping coefficient, written in the following way. Okay, first of all, in part A of the problem, we just have to do a little bit of plug and chug. So it asks us to find the angular frequency and the period. Now, the angular frequency is the angular frequency of the DHO. That's this quantity here. So let's just go ahead and plug in everything and find that value. Okay, so I'm doing so. I have the square root, first of all, of 100 divided by 1. Okay, then minus quantity, 0.25 divided by 2 times 1, and then I have to square that, and then ultimately take the square root of the whole thing. Okay, now I'm not going to round this off until later on in the number. You'll see why when we get deeper into the problem. So this is 9.9992 about radians per second. And then from there, we'll take the inverse, like so, multiply by 2 pi to obtain the period. So take the inverse times 2 times pi, and that then gives us about 0.63 seconds, like so, as the period of the oscillation. Okay, let me move the file. Okay, so now in part B of the problem, this is where I specifically take a look at the amplitude as a function of time. It says, what is the fractional decrease in the amplitude per oscillation? So in part B of the problem, now we're going to take a look at the amplitude term. Let me go ahead and rewrite it here. That is this expression. Note the exponent. Okay, what we're going to do is we're going to set the time t equal to the period. So we're going to let one oscillation go by. What this means is that after that oscillation has occurred, the amplitude that remains is going to be some percentage or fraction of the original amplitude A. Okay, let me write that percentage or fraction as x. That is, like so. So notice what I did here, first of all, on the right-hand side of the expression. I set the time t equal to a period, so one oscillation has gone by, and then therefore the amplitude that remains is some percentage of the original amplitude. And now what we're asked to calculate is that percentage. So let's go ahead and just cancel out the A, like so, and then plug in all the numbers here and then see what we obtain. So I need, first of all, the number E on my calculator. That's the base of the natural logarithm. So let me go ahead and access that. And then I plug in the following. Negative 0.25 divided by 2 times 1, and then times 0.3 seconds. So negative 0.25 divided by 2 times 1, and then multiplied by 0.63 seconds. This comes out to be 0.92. So in other words, after one oscillation has gone by, we still have 92% of the original amplitude. And then after another oscillation goes by, then we still have 92% of that amplitude, and then 92% of that amplitude, and so on and so forth as the oscillations occur. So then therefore, to answer the question as it's phrased, it says, what is the fractional decrease in the amplitude per oscillation? It's an 8% decrease. Okay, and then we do the same sort of calculation for part C of the problem, but in part C of the problem, we're concerned with the energy expression. So let me move to the lower board. Okay, so for part C, we're taking a look at the energy expression, which is as follows. Okay, note once again the slightly different exponent, however, so be careful of that. And now it says the following for part C. What is the fractional decrease in energy per oscillation? So now what we're going to do once again is take the time t here and set it equal to the period, and then on the left-hand side we're going to have some percentage of the original energy, which is the quantity 1/2 Ka squared. Once again, I'll think of the percentage as a number x, like so. So take a look at what I'm writing here on the right-hand side first. Notice that I set the time equal to the period, capital T, and then therefore we have some percentage of the original energy after one oscillation has gone by. Okay, let's go ahead and cancel out this term, and now just plug in and get this number for x. It's going to be slightly different than what we did earlier for part B. Okay, so once again, I need the base in the natural logarithm, and then it's negative 0.25 divided by 1 times then 0.63 seconds. Like so. Let me make sure I do this correctly. 0.63, there we go. And this ends up being about 0.85. So after one oscillation has gone by, we still have 85% of the original energy. And then after another oscillation, it's 85% of that energy, and so on and so on. So then therefore, it's a 15% decrease per oscillation as time goes on. Okay, now in my earlier lecture, I mentioned that when damping is taken into account, the angular frequency omega, as you can see on the top board, is slightly different than the natural frequency of the spring omega naught, the square root of K over M. Even under these conditions, however, where a fair amount of energy is being lost per oscillation, there's not much difference between the two values of angular frequency. I'm going to illustrate that here in part D of the example. Let me move the file. Okay, so it's asking us then the following. What is the percent difference between the natural frequency, omega naught, and the actual angular frequency, omega, of the DHO? So think of this as a percent error calculation for part D. Okay, let me do some erasing. Okay, so for part D, here's what we're going to calculate. Notice that I'm writing this much like a percent error calculation. It's like we're calculating the percent error between the theoretical value, or idealized value, if you will, of omega naught, and the actual value of omega when damping is taken into account. Notice that we're going to make a comparison here with respect to omega naught. When we calculate this out, ultimately it's going to be a decimal. We'll then multiply it by 100 to convert it into a percentage. So let's see what the percent difference is between the two values. Okay, now on the top board, I still need to calculate here omega naught, by the way. It's the square root of 100 divided by 1, so then therefore it's just 10. And then this illustrates why I didn't round off this number for omega earlier. Okay, it's pretty close to 10, but it's not exactly the same thing. Okay, so let's go ahead and subtract it like so, and then divide by 10. Okay, whatever this is, we'll then multiply it by 100 in order to convert to a percentage, and it's going to be, as we'll see, pretty small. Okay, so 10 minus 9.9992, and then divided by 10, multiply that by 100, and then you end up with only a 0.008% difference between the angular frequency of the DHO and the angular frequency of the SHO. So in an experimental laboratory setup, when involving springs, for example, usually in simple laboratory setups, damping is not taken into account as a source of error. And the reason for that is because there's only a minute difference between the two quantities of omega, the angular frequency, even when damping is taken into account. Okay, that concludes the DHO.